Alright, so we're going to talk about, remember when we talked about electric field, we talked about Coulomb's law. That was our integration technique for calculating electric fields. And then we had a nice law that you could, was a shortcut based on symmetry, although shortcut only if you know how to do it. Gauss's law, right? So that was one of Maxwell's equations. We have an analog in magnetic field stuff called Amperes Law, which is also one of Maxwell's equations. So before we get to that, let's ask a question. So it's either going this way or it's going this way. Okay. So let's figure this out. Which pole does this have to be? South. So that means the magnetic field inside of the magnet points which way? This way. Okay? So that means this is the north side, this is the south side. The magnetic field here points this way. In this magnet, it points this way. They point in opposite directions, so it's repelling. So if the magnetic field points this way, that means we curl our fingers this way. So it goes in at the top and out at the bottom, okay, which will be B. All right? All right, let's take a little math detour. I can tell you're all really excited. So, does anybody remember what a line integral is?
No, what is that?
Well, we're about to learn. So, how do we determine the length of this line? Just don't worry about integrals yet. How would you figure this out? Final minus initial, because it's along a straight line. So if I said figure out what the length of this line is, what would you do? Get a ruler, right? So you just measure it.
Fuck me. Okay, I guess.
Okay. We're gonna start real simple. So let's say that gives you a length L. Okay, this is not to scale, but let's say we make this line really squiggly. All right, and this is just, it could be any shape. How do you measure this?
Same, just with the string. Pieces.
You could go with a string, but we could measure the little tiny pieces, because as you get smaller, remember, individual tiny pieces are pretty much straight. So we could break it up into a bunch of little pieces, measure one piece, and then add up all the little pieces. Okay, as long as we know how many pieces. So if the line's curvy, we break it up into these little delta S's, or if you want to make them really small, call them ds, okay? And you sum up all of the delta S's. And since this is the same line as that, even though it's not drawn to scale, it should, when you add them up, they should give you L. Okay, if you make it really small, then you just integrate ds's, and those should give you L. Okay, just like when we integrated dA, it just gave us the area. Okay, you integrate dA over a whole sphere, you get the surface area of a sphere. Okay, if you integrate dA over a rectangle, you get the surface area of that rectangle. If you integrate ds over a line, you get the length of that line, no matter what shape it is. Okay? Okay, so now we want more than just the length of the line. Let's say we put this line in a vector field. And we want to know how much of this vector field is parallel to the line. How much of it lines up with the line? Well, what kind of math is that? When we want to figure out how parallel things are, including their components, right? That's a dot product. Okay? So for each of these little pieces, delta S, we say, okay, this part of the field is at this angle from delta S, right? We have an angle between them, and we make a dot product. Okay? So B dot this chunk of the line is equal to something, and then we add all of those up. All right, and we can make that an integral because delta S can become ds. We go from the beginning to the end of the line. All right, fairly straightforward. Okay, so when is this a nice integral?
And it's a line.
When is this dot product easy to calculate? When you're tangent to the line, when B is tangent to your line, right? So when they're parallel, or when it's perpendicular, okay? So if you're perpendicular at all points, what's this integral give you? 0. If you're parallel, right, if you're constant and tangent, then it gives you, well, the dot product gives you 1, right? And then you can pull out B, and then you just have an integral of dl, which is easy, right? Or an integral of ds, right? The integral of ds gives you L. You get the total length. So as long as you can pull out B, because the dot product gives you 1.
Yes. Yes.
All right.
The fucking best.
So if the magnetic field is tangent to the line, right, that means the dot product goes to 1, and then you pull out the magnetic field. If the magnetic field that you pull out is constant, you can say, okay, now that's B, and then you just have this integral of ds, which we know is L. All right? That's just B times the length of the line. Okay, so that you can see this is going to be a lot like Gauss's law, but we've changed, instead of area now, we're dealing with length. All right? Okay, so let's try this out. Yes, the answer is B. Okay? So look, along this part of the line, is this parallel or perpendicular? Parallel or perpendicular to the magnetic field? It's parallel, okay? Which means the dot product goes to 1. And look, B is constant, so you can pull out B, and then you just integrate over the length of this part of the line, which is A. Okay, so this part gives you BA. What about this part? It's perpendicular to the magnetic field, so the dot product gives you 0. So you get BA plus nothing. Okay? Just BA. Alright, how about this one?
You couldn't let us have that. We couldn't end on that note. On success.
What?
I mean, you asked him to stop teaching, then he has more free time.
No, they asked him.
Initially, I did like B.
Okay, yes, the answer is D, because look, this part gives you BA positive, this part gives you BA negative, because these are anti-parallel, so this is going to be the cosine of 180, alright, instead of 0. And these segments give you 0 because it's perpendicular, so facto, the answer is 0. BA minus BA is 0, okay? Alright, so we've just been doing this half of Ampere's law. Here's the other half, okay? What does this circle mean?
Closed.
Closed what?
Surface.
Closed loop, okay? Because it's not a surface integral, it's only got one squiggle, okay? So one squiggle means line integral. This means the line has to start and end at the same place. So for a closed loop, right, when you integrate around a closed loop, it should give you mu naught. Remember, we said mu naught sometimes hangs out by itself. Okay, mu naught, 4 pi times 10 to the negative 7 Tesla meters over amps, all right, times the current through that loop. All right, and we'll spend some more time talking about this soon, but yeah, this is Ampere's law. Okay, and so this is our magnetic field version of Gauss's law, but you'll notice this is not a surface integral. If you take Gauss's law for magnetic fields, what do you always get? Zeros. Because remember, magnetic field lines are always loops, so that means the flux through a closed surface, where loops go in and they go out. They go out and they go in. So anything that comes in goes out, and the net flux is always 0 for loops. All right, let's talk about Ampere's law. Okay, so we talked about how to integrate from a point charge, and what was that called? Biot-Savart law. So remember, for electric field, we had Coulomb's law. That was for a point charge. Okay. For magnetic field, we have Biot-Savart law. That's for a point charge. If you want anything else from a point charge, you have to integrate from the point charge. Okay. So you have to go through the integral for Biot-Savart, or you have to go through the integral for Coulomb's. All right, depending on if you want the electric or magnetic field. Now, if it's a magnetic field, what should the point charge be doing? Moving, okay? Moving charges generate magnetic field. And when we talked about electric field, we had a law that was primarily based on symmetry, okay? This is a sort of vector calc. This is sort of a vector calc thing that says, remember, with Gauss's law, what did we integrate over?
An infinite.
A surface, a closed surface. It was a double integral, it had that circle around it. Okay, so when you integrate over a closed surface, you would get what?
Charge density?
Well, what was it dot product with?
Area?
Remember, Gauss's law, let's go back a little bit.
Oh, yes. It was the constant, and you pull that out, and then yeah. Gauss German? I would bet. Sounds like something that they do. Gauss. Especially because it's bad grammar.
What's this?
Electric field dot with surface area.
Yeah, but what physical thing is that?
The flux.
Flux.
What I heard you say.
Electric flux. Okay, so the electric flux is the dot product of E dot dA, right? Integrated over a closed surface. So we're talking about the flux through a closed surface, so the divergence through a closed surface. So is the vector field going out or coming back in? And remember, the vector field for this Q enclosed is because, okay, if you have a charge enclosed, we know the field lines either go out or come in, depending on whether it's a positive or negative charge. So this is telling us something about the vector field. This tells us the flux, and we know flux has to come from a source, okay? And it has to come from a singular source. It has to come from a positive charge or a negative charge, because that's where electric field lines start and end, okay? Electric field lines can start someplace and end someplace. What do we know about magnetic field lines?
They're going to circle.
Loops
and
They
spirals.
always start and end in the same place because they're circular, okay? So if we did the same thing for magnetic fields, so let's say flux, magnetic field is B dot dA, okay? What's this going to equal? Zero, right? Because this tells you how many of the field lines are either there's like a net amount of field lines going out, or there's a net amount of field lines coming in. But if you have a loop, what goes out always comes back in. So that means because we don't have monopoles, because we don't have the equivalent of a positive or negative charge that we can break up, right? Because of that, we cannot have a net flux from a magnetic field. It's always got to be zero, okay? So this is some interesting asymmetry in these two fields. We know they're related, but they behave a little bit differently. And this comes down to, when you cut a magnet in half, can you get north or south by themselves?
No.
No, just a north pole, just a south pole, that doesn't happen. You cut a magnet in half, you get two magnets, both with the north and south pole. Okay, so there's no magnetic monopoles. But we do have a way of doing a symmetry law that's a little bit different. So we're going to have Amperes Law, and Amperes Law says if you integrate around a loop, not a surface, right, over just a loop, because remember, this is just one integral, okay? So this is a line integral. It's a one-dimensional shape, okay? Surface integral, 2 dimensions. Line integral, 1 dimension. And I know you're going to be like, well, actually a circle is 2-dimensional. But if you integrate around the circle and you just stay on the circle, you're only using 1 dimension, okay? You're staying along a line. So line integrals are 1-dimensional. You integrate around a magnetic field line, essentially, okay? And we know those are circles, okay? So you integrate along a magnetic field line, all the way along it, from the start to the end. That is a loop, all right? Then it's going to be equal to some constant times the current through the loop. All right? So geometrically, this looks something like this. An I through is just the net current through the loop. Okay? So it's sort of like if you create a circle and you have current flowing through it, right? You're just looking for how much current gets through your circle. And you can see this is going to get complicated if you want to see what the magnetic field is like inside a wire, and you'll have to use density again. But same basic idea as Gauss's law, we've just changed dimensions, yes?
Is there a reason I3 is going the opposite direction?
Yeah, so the directionality of the current matters, and so when you would do this, you would have these would have different signs, okay? So this is just an example, but this is the full thing. So this is the line integral around a closed curve. Now, generally, you want to make your curve parallel or perpendicular to your magnetic field lines. Okay, and we'll go through some examples. This is the total current passing through the closed curve. All right. So the way you want to do this just the general setup. You draw a picture, you choose your path, okay? So you want to make sure that you can make the dot product go away. Then you determine whether the currents going through the path are in the positive or negative direction, and then you use Ampere's law to calculate B, okay? So we spent the first 2 chapters calculating which field? Electric field. So we were calculating E, lots of different ways to calculate E, and then relating E back and forth to electric potential, and all of that stuff led to force and energy again, okay? Then we worked on circuits for a few chapters, and now we're talking about how do we do the exact same things for magnetic fields. Okay, so these are the same techniques we used in the first 2 chapters with just some minor tweaks. All right, so we're going to spend this chapter and next chapter calculating magnetic field, and then we're going to talk about how electric and magnetic fields are directly related. All right, so let's start by doing an example. We'll do this one together.
So here we have my very poor drawing of a wire. It's got a radius R, and it's got some current going through it. And we'll call that I. So we want to figure out what the magnetic field is inside the wire. Now you know, since this has actually got a bunch of current coming out of it, sort of like this, the magnetic field should look like a round thing that goes around the wire, so a little bit like this, and then maybe out here. But we're going to have to, we know what the shape of it is, but we want to actually calculate it using a formula. So in order to do that, we're going to have to use Ampere's law. And Ampere's law looks like this. Now you notice this looks a lot like Gauss's law, except this only has one squiggle, one integrand, and it's still a circle, but this doesn't mean a closed surface anymore. This just means a closed loop. So you're not drawing a three-dimensional shape, you're drawing a line that connects at the ends. It's still a dot product, and since we know that our magnetic field inside the wire probably looks something like this, we probably want to draw our loop in that direction. So let's pick an Amperian loop. And we'll pick an Amperian loop that we know is going to be parallel at all points to this magnetic field. So here's our Amperian loop. All right. It encloses some of this current, but remember, this whole thing is just a solid thing of current. So our Amperian loop has a radius we'll call small r, and then we'll rewrite our whole setup here. So this is B, and since they're parallel, that means that goes away, so that's ds. It's still a loop, so we still need to include this, but the dot product's gone away and you don't have to treat these as vectors anymore. Then mu naught I enclosed, okay? Or I guess better to write I through. Well, what's going on with current through? Well, the total current takes up this much space. But the Amperian loop only encloses this much space, okay? So we want to figure out what fraction of the current gets through that loop. Now, like before, we just need to use density. So the current density, J, is I over pi r squared. And then the area that's actually enclosed, that's going to be pi little r squared. So when we calculate our current going through, we use J total times A enclosed, and that's going to be I over pi r squared times pi little r squared. Well, you can see these cancel. You get I r squared over r squared. Okay, so you plug that in over here. You have b ds is equal to mu naught I r squared over r squared. Now, over here, you can pull out b because it's constant, and then you just have ds. But ds is just the length of this loop now because you're just integrating around this curve. So this is 2 pi little r mu naught I r squared over r squared. Well, you can see one of these goes away, and you end up with b is equal to mu naught I over 2 pi r squared r. And this is all constant, so you can see that b is going to be linear in r, which makes sense because as you make this loop bigger and bigger, you're going to enclose more and more current, and that's going to make your magnetic field bigger. So just to go back through, all the things that have to do with the Amperian loop look like this. So this is enclosed, enclosed, so that's enclosed. This is part of your total. And so you end up with something that looks a lot like a linear function. Now that's only true once you're inside the wire, and then next we'll do outside the wire. Now we're going to use Ampere's law to figure out what the magnetic field would be outside the wire. Now we already kind of know the answer to this because we know that when we have any kind of wire, we curl our fingers around and our magnetic field looks something like this. Okay, but we need an actual equation. We already know the direction. So when we have this magnetic field, we once again want to use Ampere's law. So Ampere's law looks like this. It's a line integral of b dot ds mu naught I through. Okay, so once again, we want to pick a loop, and let's pick our loop to match the direction of the magnetic field. So here is our loop, and here is our magnetic field. And then in this case, it gets really simple because the current through is just all of the current. So when we rewrite this, we can see these are parallel, so you can get rid of the dot product, and B should be constant because it's the same distance from the wire, so you get B ds is equal to mu naught I. So I B ds. Okay, this becomes b 2 pi. Remember, this has a distance r. That's our changeable radius, so 2 pi r is equal to mu naught, just all of I. Okay, so b is equal to mu naught I over 2 pi r. And unlike before, when you were inside the wire, now outside the wire is going to be inversely proportional to r. But this is also what we'd found from Biot-Savart law. We know B for an infinite wire is mu naught I over 2 pi r. And hey, look, that's what we got. So this is the result, same result we got before. So Ampere's law works on something we know.
Brings us to a coil of wire. You have one of these in the car. Okay, in the starter. It's a coil of wire. It's called a solenoid. Coils of wire are important. Why? What does a loop of wire act like? It's an inductor. It creates a magnetic field. Okay, remember one loop of wire created something that looked like a bar magnet. Okay, a similar field. So if we want to make that magnetic field stronger, add a bunch of loops. Okay, so the way that you create a magnetic field is with a coil of wire. The way you create a constant magnetic field is with a coil of wire. Okay, how do we create a constant electric field? Capacitor. Okay, so the solenoid, or it's also called an inductor, all right? It's also called a coil of wire, but that's a less technical term. That's how you create a constant magnetic field. Okay, so this is a coil, right? This is a conductor with current passing through it. So the current goes in here, it comes out there. Okay, we're going to use Amperes Law to figure out what the magnetic field is going to look like inside the solenoid. All right, so I'm going to erase this.
It's like those old mad scientists, like shit that they have in their lab, but like something like flies through it and drops out the other end. You know what I'm saying?
Oh, like
some
yeah.
lizard shit.
All right, so we're going to start by this. Let me draw this.
Like a spring.
Yeah. It's going to be ugly. So we have current going in here, current going out there. So this is current in, current out. Okay? I'm going to draw this a different way. I'm going to figure out what's the best way to make this understandable. So let's say you have this thing and you saw it in half. Okay, because we want to be able to see inside the solenoid. Right? So I'm going to draw it like this. So here's the different coils. We're just looking at,
Like a bisection.
yeah, this is like a cross section. So, yeah. It's not the best drawing, but you can see
It's like a xylophone.
All right.
Or that,
So-
depending on how hungry you are.
So you can see the way this is drawn, the current's coming out at the top of the page, right? So out, and it's going in over here. Okay, so that means you're going like this, right? So it's, the current's going like this. What should the magnetic field be doing?
Circling.
Circular.
So we're going with
It's going, but which way inside here?
It's gonna be through the ribs.
So if you go like this, right, the magnetic field should point this way.
Yeah.
Yeah.
Okay? So we're going to draw that. Magnetic field lines inside are pretty constant. Okay? What do these do? Well, they come out and they loop around, right? And, you get the idea, but they're going to be coming back the other way. But what do you notice about the density of the magnetic field lines inside versus the density of the magnetic fields outside?
Dense inside.
Dense inside? Are they dense outside?
No.
No, they are pretty not dense outside. You say not dense. Talking's hard today. All right, so this is the direction of the magnetic field lines. All right, and so we're going to say that outside, if you have a perfect solenoid, outside the magnetic field is pretty close to zero. Okay, because you can see inside they're pretty close together, the lines. Outside they get spread out. Okay, that's the other word. All right, so how do we want to draw a loop this time? Remember, what did we do over here? How did we draw our loop?
Parallel.
It's parallel to the magnetic field line. So what shape do you think our loop should be this time? Well, here it would be straight, right? And then what?
And then
Do you always want to be parallel or perpendicular.
And then perpendicular?
So let's try perpendicular. Okay. These are perpendicular. And then out here,
Parallel.
So it just becomes a
parallel, but what's the magnetic field out here?
It's like 0.
0, right? So here, the dot product's going to give you 0. Here, it's parallel to the magnetic field, so the dot product goes to 1, but when you pull out B, it gives you 0. Here, you're parallel to the magnetic field, and so the dot product gives you 1, and you can pull out the magnetic field. Okay? So let's look at what this looks like. We have B dot ds is equal to mu naught I through. Okay? So, let's call this length L. Okay? And this will also be length L. And are we going to even care what these lengths are?
No, because they go to 0.
Okay? So this breaks down into 4 pieces. Okay? The first one is going to be B times ds for L. Alright, so that's here. Alright, so what does that ds give us? Just L. So we have BL plus 0, that's these sides. Okay, and then this is going to be L times B, which is 0. So 3 zeros. So this one's BL, this gives you 0, this gives you 0, this gives you 0.
Why does the third one give you 0?
This one?
Yeah.
Because the magnetic field out here is 0.
Okay.
So it'll give you BL, and
But
then you
it-
plug in B.
But it's 0.
It's 0.
Okay.
Okay? Alright, mu naught, how many, so each of these has a current I running through it, so how many currents I do you have?
4.
1.
Well, how many times does the current go through?
Twice?
2. So this would be 2I. You can also call it Ni, because any of these things, right, if we draw this loop, no matter which way we draw it, we can close 3, we can close 1, we can close 2, it has to give us the same answer. Okay, so this represents how many pieces of the loop, the number n. So n can be equal to 1, 2, 3, 4, etc.
So n is a variable?
N is an integer, and n can be a variable.
Okay.
But when you're talking about a specific solenoid or a specific coil of wires, then you can figure out n by counting. Okay, and so we also want to be able to scale this up to the total n, because what's going to end up happening is B is going to be mu naught n over L. Okay, so in this case, right, what this L is going to correspond to 2. If your L gets bigger,
Then it becomes...
right, it's going to correspond to more loops. So what we want is, we want this to be the total L, this is our total N and our total L, is going to be the same as the ratio between this N and L. You see what I mean? So this is the density of the coil. And obviously, if you put the loops closer together, what do you expect to happen to the magnetic field?
It's going to shorter.
It's going to be bigger, right? More loops, bigger magnetic field. So this is the density of loops, okay? And then just times the current.
And I
So-
just... Oh, yeah, I was like, I
So
didn't...
this thing is the tricky part, right? This is going to give you the density of loops. Now, if you're dealing with a real solenoid, what you do is this is the total number of turns divided by the total length. So if you make a solenoid and it has 5 turns and it's 1 inch long, that's just 5 divided by 1. Okay? So we just scale it up, but we can do it for any density. Yes?
5 turns, like 5 coils.
5 quotes,
Okay.
5 loops. So you just measure the length of your solenoid,
And then
right?
divide
That's
it.
L.
And then
And
divide
then
it.
this is the number of turns. Yeah, so N divided by L gives you the density of loops. So this is the magnetic field for a solenoid. Alright? And it looks something like this.